Diamonds, nature's epitome of elegance and splendor, hold an unrivaled stature in the world of gemstone, appetizing opulence and grandeur. These shimmering stones carry worth beyond their striking appearance. Their societal and historical significance amplifies their allure and marking them as globally coveted treasures. The shape of diamond plays an important role in determining its value in the gemstone market. This particular contour and facet arrangement directly affects the diamond's sparkle. Additionally, some shapes align more with current market trends and cultural inclination, often commanding higher prices. Thus, a diamond shape is linked to its aesthetic appeal, functional quality, and market desirability. In an industry that demands precision and reliability, the need for an automated recognition of diamond shapes has never been more pronounced. Automating this process promises an unparalleled standard of consistency, speed, and objectivity, driving forward the gemstone industry into a new era of technological sophistication. The shape and cut of diamonds play a pivotal role across several industries, from jewelry manufacturing to rigorous process of diamond grading and stringent quality control. Traditionally, recognizing these shapes has largely hinged upon expert analysis. While the expertise of these professionals is invaluable, it introduces a subjective element into the equation, making room for potential inconsistencies. But the implications run deeper. Beyond just subjectivity, these traditional methods are considerably time consuming. And here's the catch: the accuracy and efficiency of shape recognition doesn't just affect the classification of diamonds, but has direct ramifications on the value and overall quality of the final diamond product that reaches the market. In today's age of rapid advancements, it is crucial to ask, can we do better? The realm of deep learning, with its revolutionary algorithms, offers a beacon of hope. Techn- Techniques like convolutional neural networks and recurrent neural networks present potential solutions to enhance the accuracy, efficiency, and most importantly, the objectivity of diamond shape recognition. With the advent of deep learning algorithm and sophisticated algorithms, the potential for pinpointing accuracy in shape recognition increases significantly. Systems can be trained to recognize nuances and details that might be challenging even for a seasoned expert. Automated process can evaluate diamonds in a fraction of the time it would take a human expert. This efficiency doesn't just translate to faster result, but also to cost savings in the long run. While expert analysis is invaluable, it is still susceptible to human error. Fatigue, oversight, or even external pressures can influence judgments. Automated systems can help mitigate these errors. In summary, while traditional expertise in diamond shape recognition will always hold its value, the integration of modern technology approach is imperative to address the challenges of today's global and rapidly evolving diamond industry. Now let's look at the figure on the slide. Here we see a spectrum of the most recognized diamond shapes. There's the round brilliant, capturing light and hearts with its impeccable symmetry. Then we have the edgy princess cut, a favorite of contemporary designs. The emerald shape showcases grandeur with its broad open facets, while the pear shape gracefully merges the round and the turquoise silhouette. But why does this matter? The shape of a diamond doesn't just dictate its external aesthetics. It deeply impacts its internal play of light, thereby determining its brilliance and value. When the consumer selects a diamond, they're not just choosing a shape, they're choosing a story of light, reflection, and personal aesthetic. Determining these shapes and their quality was an art mastered by human experts. Visual inspections by seasoned gemologists focused on the facets, the symmetry, and the proportions. The beauty of a diamond was discerned through magnifying loupe and an expert eye. Now let's delve into the specialized world of gemology and the tools that make precise diamond identification and analysis possible. The gemnologists employ a unique arsenal to inspect gemstone. Starting with the loupe, this isn't your everyday magnifying glass. It offers an intimate view of gemstones, revealing details invisible to the naked eye. The polariscope is another fascinating tool. It sheds light, quite literally, on the optical nature of transcrystalline gemstones, giving insights into their internal characteristics. Ever wondered what the rainbow in a diamond? That's where the spectroscope comes into play, breaking down light to reveal a gem's spectral colors. The dichroscope has a very niche function, primarily helping gemologists discern the refractive properties of gemstones. Lastly, the mysterious glow of some diamonds give off under UV light isn't just a party trick, it's a valuable identification feature. Venturing into the realm of advanced imaging, techniques such as 3D scanning and photogrammetry aren't limited to Hollywood movies anymore. They're helping gemologists capture intricate details of diamonds, making identification even more accurate. And that is the present. Now, what about the future? It's digital. The field is pivoting towards automated methods with advanced in computer vision and machine learning, especially with methods like neural networks. We are on the cusp of creating algorithms that can identify and classify diamonds just from their images, a testament to where technology is taking to us. The blend of traditional expertise with modern technology is revolutionizing the way we understand, classify, and value gems. CNNs made up of four essential layers: convolution layers that detect features like edges, pooling layers that reduce dimensionality, fully connected layers for processing the features, and finally, classification layers like softmax that categorize the image into one of the predefined classes. Key CNN architectures are LeanNet, the first architecture that set the stage for CNNs; AlexNet, notable for its deep architecture; VGG, known for its small use of small receptive fields; GoogleNet introduced the inception module; and ResNet solved the vanishing gradient problem with residual connections. Each of these architectures has its own set of innovations and achievements that have pushed the boundaries of CNNs of what it can do. In summary, understanding the basics and the key architecture of CNNs gives us the groundwork to implement advanced and effective models of diamond shape recognition. Now, I'm going to introduce you to the incredible world of recurrent neural networks, or RNNs as they are popularly known. You may wonder why the hype around RNNs. Well, a traditional feed-forward neural network takes an input, passes it forward. However, imagine a network that has loops, enabling it to remember its previous state. This is precisely what an RNN does. This concept was first introduced by Williams and Zipser back in 1989. Lee Kung, Bengio, and Hilton, in their 2015 study, emphasized how deep learning is revolutionizing computer vision. But what sets RNN apart from the deep learning pack is their exceptional talent for processing sequential data. In layman's terms, RNNs have an uncanny ability to recognize patterns that unfold over time or space. And that's not all. Their potential extends far and wide. In the medical domain, RNNs are making waves. 2019 study by Chang and his colleague presented an RNN method anchored in the short-term and long-term memory structure known as LSTM. This RNN adaptation has significantly trimmed down the costs associated with labeling cells. The result? Speeding up the real-world application of cell classification. Moreover, when these RNN models apply to building image datasets, the possibilities are vast. Now, while RNNs sound magical, they've had their fair share of challenges. And that's where the evolution comes in. LSTMs, for example, introduced by Hochreiter and Schmid-Duber in 1997 addressed a pesky issue in Rnns known as the vanishing gradient problem. The Elastians are a marvel because they have the memory cell that remembers things for longer duration. This unique feature enables them to capture patterns for long from long ago. But the innovation didn't stop there. In 2014, Cho and his team introduced us to GRUs. Think of them as Elastian's younger sibling. They have a structure that's simpler, which makes them computationally less taxing, especially on smaller datasets. For our studies, given the advantage Elastians bring to the table, we are leaning towards using them, especially in our endeavor in diamond shape recognition. RNNs are not just a topic of academic interest, they are a testament to how far we've come in the field of neural networks and deep learning. Their evolution from basic RNNs to Elastians and GRUs and the expanding range of applications from medical and sector to gemology is nothing short of inspiring. Our dataset has images representing 8 distinct diamond shapes: cushion, round, oval, heart, turquoise, emerald, pear, and princess. Each shape exudes its own elegance and brilliance, and a model's task will be to identify these nuances. Each of these diamond shapes has its own dedicated folder, and within these folders, every image is tagged with a unique identifier to ensure no mix-ups. The image format is JPEG. The image is a snapshot of the diverse diamond shapes the dataset comprises. This visual will give you a glimpse of the variety and depth we are working with. For the EDI analysis, the data distribution analysis showed an imbalanced class, where some classes like cushion and round had more samples, while the heart and turquoise had very little. To fix this, we had to do data augmentation techniques and also do some random sampler methods. Image analysis showed that all the images were of uniform size, which would mean very good for model training. Image color analysis was another analysis that showed that the class had a diverse set of colors, which again will contribute to very good model training. Now I'll walk you through the vital steps we've taken to ensure our data is primed for stellar results. When analyzing a dataset, we noticed some classes of diamond shapes had more images than the others. A balanced dataset is pivotal, so as it ensures a model doesn't develop a bias towards frequently represented classes. By addressing this imbalance, we're setting our model up to generalize well across all diamond shape, ensuring fairness and representation. All our diamond images maintain a consistent size of 300 by 300 pixel. This uniformity is a boon. It means we sidestep the complication of resizing images, which often can distort vital information. Next step that we took was pixel normalization. We normalized the pixels of each and every image by dividing it by 255. While this may seem like a minuscule step, it's monumental for a model. Bringing pixel value to a range of 0 to 1 ensures our deep learning model converges faster, setting the stage for efficient training. We also have the option of jazzing up a dataset using techniques like rotation, zoom, and flipping. Data augmentation introduces diversity. By representing the variations of the same image, we fortify our model to be more robust and versatile. It's imperative to gauge how well our model will perform in the real world. To do this, we split our dataset into separate chunks for training and evaluation. This ensures that our model has learned from the training data. It's then tested on completely unseen data, giving us an unbiased measure of its powerness. And then comes one-hot encoding of labels. To the uninitiated, a one-hot encoding might seem like a tech jargon, but it's quite straightforward. It's a way of translating categorical data like diamond shapes into a format that's uh, accessible to our model. This transformation simplifies how a model interprets predictions, ensuring clarity and precision. Remember the imbalance we talked about in the beginning? Apart from data augmentation, another tool at our disposal is oversampling. By creating synthetic samples for underrepresented classes, we again strive for balance. This ensures a model doesn't play favorites and performs uniformly across the board. In conclusion, these steps underscore our commitment to creating a great dataset. Now we'll discuss our model's architecture and some essential training techniques we've applied to ensure the model's accuracy and performance. Let's start with the architecture. Our model uses a Keras library with TensorFlow as its backend. Keras provides a simplified interface that makes model creation and configuration easier. The model is structured with several layers. It has a convolution layers activated by the ReLU function, which is widely used in deep learning to introduce nonlinearity. Next, we have max pooling layers that reduce the dimensions of a data, making the subsequent process more efficient. Further into the model, we have dense layers, followed by a dropout mechanism to help reduce overfitting by randomly ignoring certain neurons during training. The final output of a model uses a soft max activation function. This produces a probability distribution across all the classes for each image. For Rnns, at its core, our method revolves around using LSTM models, a special type of recurrent neural network. What's fascinating here is how we discuss or how we process sequential data extracted from flattened images. Our goal is to discern diamond shapes by deeply understanding the spatial relationship between pixels and spotting the distinguishing patterns. As many of you might know, RNNs excel with sequential data. Our images initially exist as three-dimensional arrays, vividly capturing 300 by 300 pixels in RGB channels. The challenge here was reshaping these images. Through a transformation process, each image is streamlined into a 1D array primed for RNN ingestion. For the architecture, the backbone of our solution is a sequential model. This setup enables us to efficiently stack layers. The main layer, or the main hero in our process, is the LSTM layer, which houses about 128 units. With, with the ReLU activation function at its disposal, it masterfully captures long-term data dependencies. Following LSTM, we introduced a dense layer that corresponds to the number of diamond shape classes we have. The softmax activation function in this layer ensures our outputs are neatly transformed into class probabilities. A convolution neural network consists of three convolution layers with filter sizes of 96, 160, and 128, all using 3 by 3 kernels and activated with ReLU. Each convolution layer has a corresponding max pooling layer, each with a 2 by 2 pooling size. After processing, we have flattened layer followed by a dense layer with 448 neurons. A dropout layer is added with a 0.5 rate for regularization. At the end, we conclude with a dense layer with 8 neurons representing diamond shapes activated by softmax function. In numbers, our model contained a total of 16 million trainable, or if not actually 17 million trainable parameters, achieving an impressive validation of 0.99%. In summary, this architecture was both efficient and effective in diamond shape recognition. For the model evaluation, what we used was the confusion matrix and the classification report. The confusion matrix is a table that is often used to describe the performance of a classification model on a set of test data for which the true values are known. Each row of the matrix represents an instance in a predicted class, while each column represents the instance in an actual class. As you could see from the table over here about the confusion matrix, it shows that the model has performed very well on the test data. It achieved high accuracy for most of the classes as indicated by the large numbers on the diagonal. Only a few misclassifications are present, and overall the model seems to be present in predicting the diamond shapes. The classification report generally provides a detailed evaluation of the multi-class classification model's performance on the test set. It represents several factors for each class as well as overall metrics for the entire dataset. The classification report shown here shows that the model achieved outstanding performance on the test set, correctly classifying all instances for each class and achieving perfect precision, recall, and F1 score. This indicates that the model is highly accurate and effective in predicting the diamond shapes. Now I'll be presenting an in-depth analysis of our RNN model, where we delve into its architecture, evaluate its performance, and understand the challenges faced. Let's begin with a broad overview of our RNN model. The architecture primarily comprises of LSTM, dense, and dropout layers. Although it has a moderate number of parameters, the model's performance on the validation set and test set stands at approximately 13.7 and 13.2%. Going deeper into the architecture, our model is sequentially structured. The first layer is an LSTM layer with 64 units, designed to handle input shapes, typically in the structure of batch size, sequential length, and input features. We also utilize some dense layers with 256 neurons and another with 8 neurons, incorporating soft max activation for our output. A dropout layer at a rate of 0.5 is also included to prevent overfitting. In terms of parameters, a model has a total of 150,536 trainable parameters. There are no non-trainable parameters, ensuring that every aspect of a model learns and adapts during the training phase. Now let's move on to the evaluation of our RNN model. Our confusion matrix analysis points towards a significant class imbalance. There's a bias, particularly towards predicting the overclass. This has resulted in a majority of incorrect predictions across classes. As you can see from this image of the confusion matrix, you can observe that most predictions veers towards the overclass, resulting in high misclassification rates for other diamond shapes. The classification report further reiterates the model's problems and challenges. Across the class, the precision, recall, of FN scores are considerably low. This data emphasizes that our current model struggles to differentiate between the various diamond shapes effectively. To visualize this, if you look at the classification report table, you can see that the weighted average FN score is just around 3%. This underscores the need for model optimization and possibly addressing the class imbalance issue. In this slide, we'd like to present our findings from, from our deep learning study focused on diamond shape analysis. Our aim was to dissect and understand the capabilities of two powerhouse models, the convolution neural network and the recurrent neural network. For the CNN model, our structure combined convolution layers, max pooling layers, and dense layers. The results? Outstanding. With nearly 17 million trainable parameters, our CNN achieved a valuation accuracy of 0.999, showcasing its robust ability to identify diamond shapes with precision. Now, for the Rnn model, although we used LSTM-based model that was suitable for time series, the Rnns performance was lackluster, with accuracies around 13%. A noticeable bias emerged, classifying most diamonds as oval, highlighting potential issues that we need to address. In conclusion, for image-based tasks like diamond shape analysis, CNNs prove superior. While RNNs have the potential in other areas, our study underscores the importance of aligning models with specific tasks. As we arrive at our concluding slide, I want to invite you on a journey into the future of gemology, driven by the power of deep learning. First, while we delved into CNNs and RNNs during our research, a large universe of deep learning architecture is still largely untouched. We have transformers, known for their groundbreaking results in natural language processing, capsule networks that hold promise in handling spatial hierarchies in data, and autoencoders, masters of data compression and generation. The potential here is immense, and the question is, what could we do over here? Moving beyond the shape of diamonds, we could also start investigating into other gemstones. Rubies, sapphires, emeralds, all these are all waiting to be explored. And in addition to that, let's consider color, the heart and the soul of any gem. The success we've seen with CNNs in classifying diamonds prompts us to dream bigger. What if we could develop an automated system powered by deep learning to identify and grade the color of any gem? While today's discussion marks the end of our presentation, it's truly just the beginning of the limitless opportunities that lie at the intersection of gemology and deep learning. Thank you for joining us on this journey. The future is as brilliant as the diamond sparkle.